So welcome to our presentation on identifying the best technology for your 3D vision application. So we're Teledyne E2B. We're a world-leading high-performance CMOS imaging experts. We provide differentiation to our customers with both standard sensors and semi-custom solutions. We're part of the Teledyne family, so this is a portfolio of technology companies. And well, my name is Nicolas, and I'm a 3D vision specialist at Teledyne E2B. So what's 3D vision? Well, 3D vision is a very broad term. It's very trendy lately. It has a lot of applications that can go from warehouse automation down to semiconductor automated inspection with nanometer precision levels. But in the end, all of these applications can be boiled down to a set of requirements, whether that is in terms of vision range, so how far you need to see, the field of view, also the levels of accuracy and precision that one needs to reach, the format and the speed at which the images need to be taken out of the system, also the scene characteristics, so whether the objects are very reflective, if they have textures or not, if we're exposed to other illumination sources, outdoors, indoors. Also, very importantly, in 3D vision, you have both active systems and passive. So active systems require illumination. And these illuminations might be subject to specifications, for example, for eye safety requirements. And last but not least, there's also the system characteristics, so the size, the weight, the power, and the cost of the final solution. So once these requirements have been identified, one can derive the application into a most suitable technique. So here we list some examples. Laser triangulation is a 3D technique that is very suitable for very high precision levels down to the micrometer, inspecting moving objects at short ranges. But then, for example, if one needs to go to further ranges in changing light conditions, then time of flight is also a very good option. There's also stereoscopy, very popular for middle ranges, which is a passive technology. And there's many other examples, like structured light, like multifocus, light field. But in the end, every technique is based on 4 main technologies. So the first one is the illumination system when it's an active technique. Also the optic. There's also the processing subsystem. And everything is centered around the image sensor. So now the question is, which imaging solution is going to deliver the most value? So now we're going to go through some active techniques and then a passive technique and see 2 examples of how the sensor can be an absolute game changer to deliver differentiation to the final solution. So I'll start talking about time of flight, so indirect time of flight. But first, I'd like to go through the definition of direct and indirect time of flight. So, well, direct time of flight is the most direct way to use the time it takes for a photon to go back and forth to an object to compute the 3D dimension. And it literally consists on measuring the time it takes for the photon to travel. So this implies quite a complex circuitry at a pixel level, meaning you have to have a quenching logic to restart avalanche diodes. You need to have also histogram generation. You need to have time delay encounters. So bottom line, what this means is that you're going to have either low resolution, either some compensation at system level. So the system is going to have to be a little bit complex, whether it is implementing a scanning engine, or laser beaming technologies, or very high computation capacity. So now the question is, is there a way to use the time of flight of photons without requiring such complex pixels? Well, actually, if one exposes normal photodiodes to a period of emitted pulses, and we measure the light at different instants, one can compute the distance from the measurement of each moment. And this is what we call indirect time of flight, which delivers high resolution at lower system complexity. So that's what the sensor is going to bring in iToF. Now the question is, so we've identified iToF as the best technique for your application. And what do we need in the sensor in order to deliver differentiation? So, well, there's 4 main challenges where the sensor can be a game changer. First of all, is the robustness to aliasing. So given that this is a frequency modulation technique, in the end, when we're measuring an object, the scene is sliced in regions of the maximum measurable distance. And we don't know exactly which slice is the object located at. So there's many solutions to compensate this and to mitigate this ambiguity. And the sensor is key to solve these issues. Second of all, there's also the artifact suppression. So given that we're measuring light at different moments, if we can manage that in a single period, then only if we can do that, we will be robust to artifacts in a moving scene. So the sensor has to be engineered for that. And here we see an example of a moving object where the fan blades show inaccuracies around it when the sensor is not properly engineered. And in our product, we have thought of this problem. And we're actually robust to artifacts in moving scenes. Then there's also if one needs to see objects in a wide range of distances and in a wide range of reflectivities, the sensor has to be very high dynamic range. And last but not least, an iToF system has to be an iToF sensor, has to be optimal in the use of light power. This is because to be robust to outdoors condition, we're going to operate in the drops of the sun spectrum, so 850 and 940 nanometers. And also, the raw throughput needs to be high enough to perform whichever background subtraction algorithm is most suitable to the application. So at Teledyn, we've engineered a sensor to solve and to provide differentiation with this exact problematic. So we are, thanks to our patented Hyro technology, optimal in the use of light power while maintaining precision over range. We have a very high HDR throughput, supporting up to 64 non-destructive readouts on chip for a single frame. We also have on-the-fly operation changes to adapt to the ranges. It's a high-resolution solution, so it's 0.5 megapixels, so delivering plus 23% angular resolution compared to a classic VGA. And last but not least, we wanted to go one step beyond the sensor. And so we have developed a iToF simulator where we can co-develop the solution with the customer, input any requirements at system level, whether it is the optic, the illumination, or even the sensor, to see how the precision levels distribute over the range and other signals of interest in the iToF solution. So this is what makes our Hydra 3D Plus the only iToF sensor that combines high resolution with real-time capabilities and also customized support. OK, so we've seen an example of a sensor that can be game changer in an active technique. Now we're going to go through a passive technique that is very common. This is stereoscopy. It works like human vision. We're seeing an object from different angles. And by computing 2 classic 2D images, one can generate the 3D depth map. And it's a very powerful technique for middle ranges on textured objects. Now, the challenge with this technique is going to be short ranges, because if one looks at an object from close by, the object is going to start to be a little bit blurry. So at Teledyne E2B, we wanted to solve this issue at short ranges, and we asked ourselves if there was a possibility to use the light incidence angle at pixel level instead of at camera level. And this is what our angular sensitive pixels technique is. So we post-process a layer over a classic high-definition 2D sensor. And then by processing the image through our SDK, one can generate a sparse depth map based on contrast detection. So this is a passive technology. So no illumination required. It's suitable for both indoors and outdoors, and it's completely eye safe. It's a see-through. It has see-through glass capabilities. And so the first sensor we've done with this technology is our Topaz 5D sensor. It's a high-resolution solution, cost-effective for 3D vision at short ranges. So it's a pity that the video is shrinked, but you can come to our booth, see the demo live. In any case, the ranges can start from a few millimeters, and thanks to our 2.5 micrometer global shutter pixel, it's a one-sensor approach, so you don't have to deal with robustness issues, lower cost of ownership at the end of the day. Also, it has lower 3D computation load, so we provide drivers for middle-end processing systems like Jetson Nano. And as for Hydra, we wanted to go one step beyond, and we embedded it into a calibrated module ready to use with an optic and an EPC SI2 interface. And this is our Optimum 5D product. So I'd like you to take away some points about this presentation. So the first one is that any 3D vision technique, any 3D vision application can be derived into a technique based on its requirements. And we can help you do that exercise. So if you have any 3D vision challenge in mind, you can come to us. We can identify the requirements together and make sure that we find the best solution for that. Another important point is the fact that given that there's many sensor level and system level trade-offs in 3D vision, the sensor technology is key to enable differentiation. And also, last but not least, at Teledyne, we are structured to provide both standard and customizable solutions for any 3D vision challenge. In particular, at sensor level, we have a customization toolbox. So we can work on 3D stack technologies. We have already sensors running on these. We can also adapt the filtering. Like, for example, for laser triangulation, we have shifted microlens derivatives. We can adapt the package, so ceramic, CSP, with frame, without frame on ceramic. We have patents for near-infrared sensitivity. We can embed on-chip processing. Also have patents on high dynamic range implementations on chip, and we can tailor the readout channel of the pixel to be adapted to your challenge. So thank you very much for your attention. I hope you liked it. If you have any questions related to 3D vision, we're at booth 10 at the end of hall 8. So yeah, feel free to come to us. You can also check our live demos, and yeah, see you at the show.
Okay. Thank you, Nicolas, for your talk, reflecting what we do, because I know this all because it's the same company, of course. But I give the audience the chance to ask some questions, whatever they are. They are not so much, but I would like to emphasize a little bit. Maybe you can talk about the importance of the light source. Which type of light source you think, especially for indirect time of flight? What do you think? What is the most important?
Yeah, so this is one of the reasons why the pixel pitch is very important, because the smaller the pixel pitch is in a night of sensor, the more power you're going to have to embed in the light source to be able to see objects at further distances. So small pixel pitch can be a limitation. And this is also why our Hyro patented technology is interesting, because it allows us to move the electrons faster within the pixel, so we can afford to have a big pitch while keeping the precision levels thanks to the speed at which we move the electrons. And this impacts the implementation at system level, as you were saying, for the light power required for a given range or reflectivity.
So bigger is sometimes better, right?
Yeah.
OK. Thank you, Nicola.